Alright, so this video is going to be one of the most important lessons you'll learn in calculus, and that's being able to visualize the derivative of a function by looking at the function. So recall that the derivative tells you the slope of the function. So if you have something like, just a linear function, there's your function. Well, what's the slope? It's some positive constant value because it has the same slope throughout. So you remember, you learned y equals mx plus b or ax plus b or whatever, however you learned it. And that m was the slope. Well, that m is constant all throughout the function. So if you were to grab that, this would be y. This is y of x, all right. I'm not sure what I just erased. F of x. Dear God. F of x, the derivative, and the correct notation for this, we'll go over some notation now, would be either to write d dx of f of x, or maybe dy dx, or f prime of x. There's really several ways of doing this, and I'm sure you'll see them in your class, so I'm not going to stress over the notation too much more that you understand. But what I'll do is black will be f of x, and f prime of x, I'll have in red, is just going to be that m value. It's a constant at height m, which corresponds to that for this function. So, a constant slope, meaning a linear function, a line with some slope, will give you a constant valued derivative. Now, let's say we wanted to move on, or let's actually start with the even simpler case, where we have just a straight line function, like y equals 3. Well, what is the slope of that function? What is the rise over run? Well, you can run, but there's no rise, so the slope, so f of x equals, I don't know, a, but f prime of x is 0. So the derivative of a constant is 0. Now, what about our beloved x squared? So once again, sketch it out. Now, this one is really tricky to visualize because the slope is either not constant or non-zero. So what is the slope right here? Well, if you visualize the tangent line, it's going to be sloping down. It's going to be pretty large and negative. So if we were to draw or make a point, let's just make a point, it's going to be negative and large. So maybe there's a point right there. That represents the derivative at that value. Now, as we move closer and closer, what is this tangent line now? Well, it's negative still. The function is still decreasing, so you have a negative derivative. The slope is negative, but it's not quite as negative as before. So maybe something here. Now, what is the slope at x equals 0? Well, it's flat. You can see the function is flat, therefore the derivative is 0. So we have another point right there. Now, what about as we move positive? We're just barely positive right here, so we have another positive value for our slope. And right here, we're getting really large positive values. So it's kind of the opposite of what happened on the other side. Now we've got a really large value for the slope. And you'll see for a function that was squared, we had a linear slope. So let's try and generalize this a bit. If we think of the last three examples all as power functions, this one being, some x to the second power, once we derived it, I'll write it like this, once we derived it, we took the derivative, and what that dx means is it's with respect to x. So if it was t squared, I would do d dt. This is saying with respect to x as opposed to with respect to time or with respect to y, and that's what you'll be dealing with the vast majority of the time in your early calc classes. So the ddx, the derivative of x squared was a linear function. It was, we'll just call it x, a straight line, and actually I'll just write 2x. I've already shown you that. The derivative with respect to x of x was just a straight line, remember? Just at some m value, or at this point I'll call it 1. And of 1, this is kind of, I wish I would have left a little bit more space, but the derivative with 1 was 0. So what you can think of is the derivative of some x to the 2 power was 2 times x to the 1 power. Remember, you can draw that 1 kind of invisibly. Oh, that didn't, I was trying to put quotes around that 1, but it's 2x to the 1. d dx of x to the 1 was 1, which is the same thing as x to the 0 power. And d dx, I'm going to erase this to make some space, but I'm basically going to be rewriting it. The derivative with respect to x of a constant was 0. So as you can see, each time when it went to a second power, it went to the first power. Derivative of something to the first power, it went to the 0th power. So for the more general case, let's say you are doing the derivative, or this is a slightly more general, and then we get even more general, of x to the n, some function, it's going to go to some function that's x to the n minus 1. Now what happens even more generally, if it's a times x to the n minus 1, so say that's a 5, you would have, let me make a little bit more space here, you would have a times n to the of x to the n minus 1. So you dropped that n down, multiplied it by a, and you subtracted 1, and it went to n minus 1. So 5x cubed, the derivative of that would be 15x squared. So now we've gone over basic quadratics. I'll do one more. 6x to the 7th. The derivative, or negative 6x to the 7th. The derivative of that, or the dx of negative 6x to the 7th, sorry, I kind of covered up that negative, would be negative 42x to the 6th. And so on and so forth. And you could keep deriving. You can take second derivatives, third derivatives, but we'll get into what those actually mean later. However, first, let's go over, we'll continue sketching. So this is not a traditional elementary function, but I'm just going to kind of make one up as I go. So let's say you have a function that looks like this. What is the derivative? And we'll do it in red. Well, at the beginning, there is no slope. It's flat, so it's 0. Until you get to this point, in between here and here, at which point you have a negative slope. But it's a constant negative slope. There's no curving going on, so it's down here. And then once you hit this point again, you go back to 0 because the slope is 0. Let's say, is it going to erase all of it? There you go. If you wanted to do a function that looked more like this, maybe. I should have drawn it in black, sorry. Let me redraw it. Like this. Here's our axis, which isn't really that important. But the derivative, so here it's positive, but constant. So positive and constant, we'll just draw that. Goes to 0. Now it's negative and not quite as steep as the positive. So it's going to be closer to the x-axis than the other one was. So you can see this was a more positive one than this is negative. And then here we have a curve. So assuming it's a quadratic curve, which we'll do, it's positive, and that would mean it goes something like that. It's increasingly positive. So the derivative looks something like that. I think that's it for now. We'll go over more things next time, a few more cases beyond the basic power. And just to reiterate, that was called the power rule, what I shared earlier. So if you have ax to the n, and you take the derivative, that is equal to an x to the n minus 1. That is the power rule. So I will see you guys next time when we go over a few different derivatives. Ciao.